Thank you very much, and thanks a lot for giving me the opportunity to present this here. So I should apologize actually, because the title suggests something much more general than what I'm really going to talk about. I'm going to explain to you what data assimilation means. This is a term from the geosciences, and then I'm going to speak about a very simple and very specific method of data assimilation, and I would like to tell you what mathematics can do in order to analyze this. So this is work I have done in a collaboration with Lea Orjacha and Tobias Kuna, who is also here. And my name is Jochen Broecker. And I will start with explaining you what data assimilation is. This is a term from the geosciences, but is a very interesting set, let's say, of mathematical problems. And then I will, as I said already, analyze a very specific approach, which in other communities is called synchronization. So you can regard this approach to data assimilation as a specific instance of synchronization. And however, it's going to be in an infinite dimensional context. So, and mainly I will focus on 2D Navier-Stokes. And I will actually also mostly focus on the case where we have stochastic influences. Right, so what is data assimilation really? So we assume that we have some stochastic process, let's call this Xn, and this process is usually referred to as the signal process, and it has some sort of state space, whatever. And the point is that you do not observe this process directly. You want to learn something about this process. You basically know what the dynamics are, but you do not know what the current state of the process is. So think about, let's say, the weather. So you know what the dynamics is of the weather, but you do not know necessarily the state of the atmosphere at any point in time. Or at like over the whole globe, you have partial information only. And this partial information is encoded in this other stochastic process, which is called the observation process. And this typically has a finite dimensional state space because you observe only a finite dimensional, let's say, set of variables. And this is called the observation process. And the idea is to reconstruct the current state of the signal process. So the first process Xn recursively from the information that you have up to time n, right? So you assume that you have a history of observations up to time n, but not into the future. And from that, you want to reconstruct what the current state of your signal process is, or let's say the current state of the atmosphere. So there are lots of approaches to this problem, to data assimilation, so various notions of optimality and so on and so forth. But in typical geophysical applications, there's also another concern, which is the applicability. So if you have some optimal procedure, then you usually have the problem that this cannot be implemented, especially not in infinite dimensions, because you have a too high complexity. So there's also a need for methods that are, let's say, very simple and applicable in real context. And one of those approaches is related to synchronization, and this is what I will explain now. So there's no claim on this being an optimal kind of procedure. So, but let's look at the situation. So I have a Hilbert space, and on that Hilbert space I have a dynamical system. I write this here in discrete time. And there's no stochasticity actually in the dynamical system except for the initial condition. So this is a deterministic system, and all randomness or all our ignorance comes from the fact that we do not know the initial condition. And in terms of observations, I assume simply the following. I assume that I have a projection P onto a finite dimensional subspace of the state space. So you can think about observing a few dynamical modes, a few Fourier modes of your dynamics, which is evolving in this infinite dimensional Hilbert space. Okay, so these are the observations. But I also have, can I have is this a pointer here? Sorry. Yeah, so this is, let's say, the observations I'm taking, but also I assume that they are corrupted with noise. So Wn is a noise process. You could say it's like IID random variables, and they corrupt my observations. And the aim is to reconstruct, as I already said, the underlying state variable Xn from these observations Yn. So the synchronization approach, and this is really a very simple approach, works as follows. So you Your estimates of the current state are there called xi(n), and you compute them recursively as follows. So let's say xi(n) is given. How do you get xi(n plus 1? Well, you first use your dynamics to make a prediction. And then what you do is you simply remember that you have observations, which are the low modes basically. So what you do is you retain the high modes in your prediction, and the low modes you just throw away and replace by what you actually observe, right? So this is basically a split into low modes. Sorry, the low modes are here and the high modes are here. The high modes you retain, the low modes you throw away and replace by your observations. And then this is called the update step, and then you go forward with that. Right, so this is what I already said. So now with this or any other algorithm, you can have the following two questions, I think. Well, you can have more questions, but these are the questions that I'm interested in. The first question is, how big is the error? So how big is the error between, let's say, the true state, xn, and your estimate yn? And then there's another second question, which is might call stability. So how much does your estimate xn at some time n depend on your initial guess? Like you have to start somewhere, so you make an initial guess of the state of your atmosphere, let's say. How does this initial guess actually matter as time goes forward? So if time n is very large, will this still have any influence or not? So just as a side remark, there are other more sophisticated approaches to synchronization, and what they mostly do is they use a slightly more sophisticated version of this update step. So you can see that this is sort of an operator convex combination of your prediction and your observation, and you can make this more sophisticated. You can, for instance, introduce this Kalman gain matrix K here, whereby you weigh between your predictions and your observations. And there are various ways to set this Kalman gain, but I'm not going to talk about this. I will simply assume that this gain is 1, basically. Right, so here's the example I'm mainly looking at. This is 2D Navier-Stokes on a doubly periodic domain, like incompressible Navier-Stokes and with viscosity. And actually, in fact, something I'm not writing here, but which is very easy to include is a Coriolis effect. And for this projection operator P, you could use the evaluation of the velocity field at a number of points, which for instance represent weather stations. But what is technically a bit easier is if you use projections onto a finite number of Fourier modes. So you assume that you observe basically the large scale features of the velocity field. So I was supposed to present a few videos here, but I'm not going to do this because of technical reasons, but you can check those videos. If you go to my homepage and then just simply type in pub, and then there are a few videos here where I'm exploring this a little bit, and I'm changing the number of stations, I'm changing the viscosity and so on. You can see a few funny videos, and you do see that sometimes it does actually work and sometimes it does not work. So this is not a trivial problem in the sense that synchronization will always occur. It depends on how many observations you take. It depends on the viscosity. It depends also on how big the time step is between your observations. And this is also something that will matter soon. So first, however, let's say that we are not doing everything from scratch here, but we are standing on the shoulders of giants. So there have been lots of people investigating this problem or related problems, and we are using their results. Let me just mention one here, which is a classical paper by Foyash and Prodi in 1967, where they show that the solution of 2D Navier-Stokes is basically fully determined by finitely many degrees of freedom if you observe enough degrees of freedom, right? So meaning that as time goes to infinity, there can be at most one solution of 2D Navier-Stokes that is consistent with a projection of this solution onto finitely many modes. Right, assuming, let me repeat this, that you have enough, you observe enough modes. Okay, so in order to analyze our synchronization approach, we have to look at the error dynamics. So what is the error dynamics? Is the difference between the true dynamics, which is this, and our estimates, which you can write down in the following way, evolves like this. So by the way, Q is just 1 minus P. Yeah, so this is basically the high modes, the small scale features, and P is the low modes, the big scale features. Okay, so you take the difference and analyze this, and this is the error dynamics. If you see the error dynamics, they look like this, right? So what is the goal now? You can have two goals. You can look at the average performance, like you take the expected value and the randomness here comes from the noise. Or this is what we're going to do. You can look at individual bounds, which are pathwise. So you look at how the lim sub of delta m behaves. And what you expect or what you would like to prove, this is basically the thing that you can expect to happen, is that asymptotically the error is proportional to the strength of the observational noise. Yeah, so proportional to the sigma here, which indicates the strength of the noise. And there's a prefactor here, which, well, you can't do more than having this a stationary process. What does this mean? So it basically means that these prefactors here will always be of the same order of magnitude. Yeah. So this is I think the best you can expect, that the error is proportional to the strength of the observational noise timed with something that is always of the same order of magnitude. Okay, so the absolute key. How am I doing with time actually? So what's the? I have no clock or anything. What's the time now? I have 10 minutes. Okay, that's I'm doing fine here. Great. So so the absolute key to the analysis, right, is something that we call the local squeezing property, and we are not claiming any originality here, but we have just written this in a convenient way. Okay. So in order to prove anything about your synchronization scheme in the context of 2D Navier-Stokes, or in fact any other dynamical system that you apply this approach to, is this local squeezing property. So let me pick this apart. So the local squeezing property says that the error in the high modes, so Q, remember, is the projection onto the high modes or the small scale features, is estimated by, well, the error in the high modes of the previous step times alpha plus the error in the low modes at the previous step. Yeah. So you can split the error in the high modes up into these. You can estimate this by the error in the previous step in the high and the low modes. And of course, this is of no use whatsoever unless you know that you have some form of stability, namely that this alpha is smaller than 1, right? For sufficiently small tau, which is the time interval between subsequent observations. Yeah, so this, if this alpha is smaller than 1, then this relation implies that the dynamics is, so to speak, stable as a mapping from the high modes to the high modes, or from the small scale features to the small scale features, up to another contribution that comes from the low modes. Yeah, so the low modes you have to basically take care of, and the high modes, if this alpha is smaller than 1, broadly speaking, take care of by themselves, right? This is what you have to establish in one form or another. So usually this will not hold globally. So you will never be able to prove that this holds, that you get alpha smaller than 1 kind of everywhere. Usually what you have to cope with is that this is only true for U and V being smaller than some large bound R. Okay, so this it only applies, so to speak, if U and V are on some bounded set. Right. So of course, if you do not have any stochasticity, then you are able to establish this. So what you need to prove is these so-called a priori bounds. You need to prove that the velocities do not go through the roof, right? And then if that is the case, you just set the observation interval time small enough, and you know that the whole thing is stable. But the problem, and this is what basically our contribution is, is that if you have a stochastic system, then you cannot guarantee this at all times, of course, because there might be situations where, due to the noise, your estimate and let's say the true state, or in particular your estimate, might become infinitely large, right? Because you always add noise, the noise is unbounded, so your estimate might, in principle, go through the roof, right? And our contribution is to cope with that situation, and I'm going to explain you how we do that. So the specific situation for 2D Navier-Stokes is the following. So as a Hilbert space, we just use trigonometric polynomials, right? And there's no mean flow, and this is divergence free. So this is the usual setup for 2D Navier-Stokes. And as the operator P, we take the projection, as I said already, onto the large scale features. So, and then the local squeezing property holds. This is not, as I said, proved by us, but you can glean this from a paper by Hayden, Olsen, and Titi. It holds if this relation here is satisfied. So what you see here on the right hand, so lambda is the wave number. So this is the highest wave number or the smallest scales you observe. And then I have a function here of the viscosity and the time interval between the observations. And then on the right-hand side here, I have again the wave number appearing. So you can see that if you fix the viscosity and the time and also this a priori bound here, then you just have to absorb enough modes, and then this term here will overtake this lambda to the 4. Right? So enough, basically this is telling you that you have to observe enough modes. And then for at least for Navier-Stokes, you have this so-called squeezing, local squeezing property. Unfortunately, for practical purposes, this is very, very bad because this grows very slowly. Yeah. The estimates that you get from this relationship, which is rigorous, are extremely conservative, extremely conservative. So numerical experiments suggest that you are doing way better than what this is predicting. So you need, or in other words, you need much, much fewer modes in practice than what this relation here suggests. Okay, so the world in reality is much, much better than in mathematics, in the mathematical theory, because this is just a worst case scenario, obviously. Okay, so if you have the local squeezing property, then the whole thing, the only thing you do is you iterate it, and you get this, you know, you might call this a discrete time Bellman-Grönwald relationship for the error, right? And of course, what you want to do is you want to have this factor lambda here smaller than 1. But as I said already, alpha, did I say lambda? Excuse me, alpha has to be smaller than 1. As I said already, alpha is a function of the true state and also the your estimate, and these can grow, these can be infinitely large because of the stochasticity. But as you will, you know, what a moment of thinking will tell you is that you don't need alpha to be smaller than 1 every time. It is enough if alpha is smaller than 1 on average, right? It will still lead to a contraction of this relationship here. So basically, the only thing you have to establish is that alpha is smaller than 1 on average. And this will give you the following theorem that in the context of 2D Navier-Stokes, and in the context of this specific algorithm I was telling you about, you can prove that these stochastic processes alpha n and beta n, so alpha n determines, let me repeat this, the stability of the low modes, of the high modes of the small scale features. These are stationary and ergodic. And there's a technical condition that this process beta n here, which basically multiplies the stochastic inputs, is tempered. This is, well, it's a technical condition which you need. And also now let's talk about alpha. So suppose the third moment of the noise is bounded. Of course, this is true if you have a Gaussian noise, for instance. Then if tau is small enough and lambda is large enough, that means you observe sufficiently many modes, then the expected value of alpha n is smaller than 1. And this is what you need. And this implies that there is a stationary process which depends only on sigma 0. So that whenever so sigma 0 is a bound that you set, and then for all strengths of the noise smaller than sigma 0, you have this relationship here. So asymptotically, the error is smaller than or bounded by, broadly speaking, scales with the strength of the observational noise. Right, and this is, I believe, you can't expect too much more in this context. And this is actually my last slide. So this is about the stability. Let's say I am setting up one of these synchronization schemes, and then, I don't know, one of you is setting up the same scheme, same code and whatever, but he or she uses a different initial condition, a different initial guess, right? Then what you want is that in the long run, we arrive at the same conclusion. Our estimates become more or less the same in the long run. And this is the case. So let's say here, this is my implementation, and this down here is Tobias's implementation. We start at different initial condition, but we see the same observations and we use the same algorithm. Then in the long run, we will come to the same conclusion. So in expectation, and you can also prove this individually, the error between Tobias's and my estimate goes to 0 as n goes to infinity. Okay, so I don't know how I'm doing time-wise, but I'm coming to the conclusions anyway. So the fundamental local squeezing property of 2D Navier-Stokes describes the amount of information that you have contained in the observations. So this is a way to look at this local squeezing property, which you can prove for 2D Navier-Stokes, but also for other infinite dimensional systems, for instance, reaction diffusion equations and things like that. So this can be used, as I showed you, to analyze the synchronization error in the presence of noise. And I mentioned this already, a number of ideas presented, they apply to other dissipative dynamical systems. I've mentioned a few infinite dimensional ones, but of course, if you have finite dimensional ones that are similar in structure, let's say, to 2D Navier-Stokes, such as these Lorentz system, Lorentz 63, Lorentz 96, then you can do very similar things, basically the same ideas. And in this situation, for these two systems, you do not, of course, have any issues with the infinite dimensionality. I realize that the microphone is working only intermittently, and I'm sorry about that. But I hope you did get something from this talk. And there was not too many technical problems, both in terms of the mathematics and in terms of the microphone. So let me thank you for your attention.